In this lecture we will continue our derivation of some model which give us the possibility to better calculate packing density and diameter of the yarn. In last lecture we finished with this equation. The pressure P, which compressed fibrous material in the yarn, is a function of packing. C is some constant, we assume it. Mu is a packing density of the yarn. Alpha is the areal type of twist factor, twist coefficient. Tau is relative fineness of the yarn, so that the ratio yarn fineness by fiber fineness. This equation was, in last lecture, derived from geometrical relations inside of. But the pressure as a function of packing density, we know from one of our earlier lecture about the compression of fibrous material. We derived the pressure as some Kp times this ratio, where mu is packing density, mu m is some maximum value of packing density, no too far from 1. A is parameter usually equal 1. And we also mentioned that by solving more difficult problem of two-dimensional homogeneous stress, which can be assumed like this here, comparator fiber bundle from all sides, we can obtain a similar equation, only some parameter B more is here. So we know the pressure as a function, some parameter times this ratio based on the packing density mu. We have two equations of pressure. One equation is going out from yarn geometry. Second is going out from physical model, some generalization of earlier one-week model, and so on. Evidently, these two right-hand sides must be equal. Therefore, based on equivalency of right-hand sides, we can write this equation. Yeah? This is the same as in last slide, this equation. Now we make only mechanically an rearranging of such equation. For example, on the place of alpha s, we give z times square root of s. On the place of tau, we give capital T by t, so that we obtain this adaptation. On the place of square root of s, we have square root of t by rho. On the place of quantity t, fiber fineness, we have s fiber cross section times rho. There are the trivial equations which we know usually from our lecture 1. S fiber cross section here is pi d square by d, where d by d square by 4, where d is fiber diameter. Also trivial, and so we obtain right-hand side of this equation in such form. Therefore, we can write left-hand side is same is equal to right-hand side is repeated this position. Let's continue it. We obtain this here. We can write it also in this formula. And what's here? Here is constant fiber diameter Kp, sorry, B, rho, pi, different parameters characterizing the material and technology, but no twist and no fiber count. So that we can say that for a given type of yarn, all this expression represents a common parameter Q. Yeah. And we can write, then we can write our expression in the form mu power to 2.5, because earlier was square root. Square root is also on the right hand side, therefore from mu power to 3 is now mu power to 2.5 is equal to q, some characteristical parameter of material, times z times t power to 1 by 4, a quarter. In Kechlin's model, on the left hand side is packing density only as a variable. On the right hand side is a count power to quarter. In opposite to Kechlin's expression, in which is square root 1/2. Well, using this equation in a common physical dimensions, we can iterate in such form. Now here are dimensions which I can recommend you for practical application. What is the value Q? It's, I said, is a material parameter. Based on our experiences, we can say that for different fibers and spinning technologies, the following values we can recommend to you. Of course, in more details, it's based on your special type of your material, fibrous material, your situation in your spinning mill, and so on and so on. But generally, you can use this here. Often say the values for wool yarn are a little rough because we hadn't too much experimental material. Well, you can see, for example, for cotton, combat yarn, 1.46 times 10 power to minus 7. For carded, 9.61 times 10 power to minus 8, and so on and so on and so on. Combat and carded yarn have another, because another structure, so that they have another values. For viscose fibers, for viscose yarn, for polyester yarns, I have only one. Of course, it's not produced as a combat. It means it is here in the middle in this table, because also the blends are used, and it can be blended with carded as well as combat yarn. Therefore, it is in the middle. Yeah. For open end type BD, we have then this. This equation, because not to be too dry, this my speech, I want to comment this equation. I know my students comment this equation. They are meaning that the application of this equation, or this equation and its application, is a little difficult. Therefore, they started to call it a horrible Netzkar's equation. In Czech language, it is it's a better, and therefore you have also some shortening for this horrible Netzkar's equation. It's horrible Netzkar's equation number 1, please. Number 1. It will be later horrible Netzkar's equation number 2 also. Well, so is the life in student society. An example is here shown. It's when we know yarn twist, yarn count, and give a value of Q. For the yarn, we usually on the place of mu m, this maximum value, this limit value of packing density, we use, it's our practical experiences, the value 0.8. No, 1 then 0.8. Why? Because in each yarn, although very hard twisted yarn, on the vicinity around surface of the yarn, the packing density is smaller. Then the mean value of packing density, also in hard twisted yarn, is a little smaller. It's not too near to value 1. Therefore, based on our experiences, we can recommend to use on the place mu m 0.1, and for A, also based on our experiences, value 1, so that we obtain then this expression which we use in practically. Well, when we know yarn count, when we know yarn twist, no problem to calculate using such equation the packing density. No problem. We can calculate the right hand side of our equation. And now we need to solve the question which mu on the left hand side corresponds to our right hand side value. We have more possibilities how apply it in practice. You can prepare tables of left hand side of our equation. So mu and left hand side value like this here. Yeah? Mu and left hand side of prepare such table. When we know value of right hand side, it must be equal to left hand side. Then we from this table can say which of mu is corresponding to our equation. Second version is use a numerical method. For example, interval splitting method. But you need know the numerical, some basic tools from numerical mathematics, and you'll be able to program it. Maybe you are, but a lot of people are not, especially in textile industry. Therefore, also the third version for practical application is possible. When we know the packing densities of our yarns produced lie around a value, some value mu star. What I mean? When you produce cotton yarns, carded cotton yarns in your spinning mill, then you know that packing densities in all of your yarn will be maybe from 0.4 to 0.5. Yeah? So you can say it will be not too far from value maybe 0.45 or 47. Yeah? Your yarn will not have packing density 0.2, for example. It's a question of maybe of other products, yeah, rowing, for example. So that we can say, okay, my yarn are near with packing density are near to some value mu star, which I will choose based on my experiences. And then it is possible to use an approximation. The approximation function to our original function. This is our original function. Yeah? The approximation which is valid around our packing density mu star, we obtain using following recipe. We calculate the value B, then value C, then and when we have this here, we calculate packing density mu using such expression. It is very easy. Now it is constant times twist times yarn count power to 1/4 all power to b by 2 by b minus 0.5. Yeah. So the yarn diameter is square root of 4 times 2 by pi mu rho. From d we obtain this expression. Practically very easy. When we realize that it is constant times t power to something times alpha power to something. the type which was derived earlier as an empirical expression. Now it is shown that it is an approximation, regular approximation of theoretical equation. Here is an example which for approximation for the Cartesians is often possible to use this equation for calculation of packing density, then diameter is evident. Well, how is the relation among between experimental result and our model? The first scheme, the first graph, show the relation on the abscissized twist times Young count power to 1/4, a quarter, and the ordinate is packing density mu. Using Q, this value, we obtain the original curve as this thick line. This is the thick line. By the way, our approximation function is this thin line. We measured a lot of carded cotyledons, diameter of these carded cotyledons, and we obtain from this measurement packing densities which characterize the points here on this graph. So you can see that the thick line follows the tendency of experimental values very well. But because because the yarns are only roughly from this value 1000 or something, 100,000, from this value know for very small packing densities from, I don't know, this is 35 for extremely small twist in the yarn. Because the yarns are not in whole region of whole area in this graph, the approximation curve, which is precise only in our point mu star, mu equal mu star, is enough good for whole interval of yarns, for example. But it is not good for rowings, for example. Here the difference is very high. My colleague, earlier colleague in the research institute, Mr. Zalaba, measured also the diameters of rowings. His empirical equations of rowing diameter, the result of it are shown in these two short curves here. You can see that it is very far from our approximation, but very near to our theoretical curve. So our theoretically derived curve is valid in an acceptable comparison with experiment in whole region from rowing to twisted yarns. The approximation equation, when you use the characteristical value mu star, when you choose this for yarn, is not possible to use for rowings and opposite. How it is with relation of packing density? Here is approximation by original, this ratio. You can see that in this region, it is very, very small difference. Yes. So we derived an equation for calculation of fiber packing density inside of the yarn. The equation in which the influence of compression or generalized van Wyck's equation was used. The same equation is possible to rearrange and to obtain the second equation, which can help us to find the best, not the best, but good value of twist of the yarn twist, suitable yarn twist. Let's start now with the rearranging of our equation to the second form, which is good for such work. Schematically, this is a yarn cross section. Diameter of our idealized, of course, yarn is d. But the axis of peripheral fibers are lying on a little smaller diameter. In the moment, I call it d dash. Yeah? We will find the ratio d dash by d. D dash by d, this ratio, found Mr. Schwarz at first, therefore it is known in literature as a Schwarz constant. Let's imagine, first step of our idea, let's imagine the yarn with limit packing density. Then the fibers are mutually all in contact. The part of the structure seems like this here. D minus d dash, this diameter d is the diameter d, sorry, is this. Diameter d dash is this here. D minus d dash in this case is equal to 1/2 of fiber diameter. So that d is, this is 1/2. On the other side too, so both together, d minus d dash is d. CD is d dash by d, so it is this here. Then it is this here, using on the place of d 4 times s by pi mu. Mu limit, now we speak about the hypothetical yarn having a limit value of packing density. Yeah? So then, after rearranging, so on the place of s, ds squared by 4, it's rearranged, so it is this here. D by ds, you can see from lecture 1, it is 1 by square root of tau. So we obtain this here. And finally, because mu lim, we know it is something over 0.9, we obtain 1 minus 0.952 by square root of tau. And because it is a little rough theory, we can, without too high error, say approximately that CD is 1 minus 1 by square root of tau. When we use tau as a t by small t, CD is 1 minus square root of small t by capital T. Yeah? Well, it was derived for yarn having a limit packing density. And when we go back to our real yarn, packing density is smaller, we can say that all linear dimensions can be elongated in the same percentage, so that also in our real yarn, roughly, this ratio can be same. So that this quantity, CD, we will use as an expression for our Schwarz constant. Well, on the diameter d dash, where are lying axes of our peripheral fibers, the axes of peripheral fibers have a little other angle than beta d, our earlier beta d. This angle is beta dash. And what is valid tangents beta dash is 2 pi d dash by 2, its radius, times that d dash after rearranging this, so that it's kappa times Schwarz constant. Yeah? Well, now let's rearrange our earlier equation 1. This equation. Let's rearrange. This is our earlier equation. Z times t power to a quarter. T power to a quarter is here. Z, it's pi dz by pi by d. It is. I multiply and divide by pi d. D, we know is square root of 4t by pi mu rho. So we obtain this expression after graphically rearranging this expression with black symbols. Kappa from this expression is tangent beta dash by CD. Tangent beta dash by CD, so I obtain this here on the right hand side. So left hand side is this here. It's the using CD on the earlier, based on our earlier derivation. We obtain this expression, and Q times tangent square beta dash times rho, maybe yes, by 4 pi means this quantity. I will call under the symbol R. Yeah? Because here was on right hand side mu, and this mu power to 2.5 was on the left hand side, therefore here is another exponent. It's 1.5 only. So we obtain our equation in this form, where R is this here. In this moment, it's no more than only a rearranged form of our earlier equation, nothing new, only mathematically rearranged. The new will come. We can study how is the quantity R. Let's think the ions from the same material and simultaneously for same or analytical end use. We will study two special cases. Case 1, the same technology and different ion counts. Example, carded cotton technology, but 1 times 20 tags, 1 times 40 tags, 1 times 60.5 tags, and so on. The second case, which we will study, is different technologies and the same ion count. For example, of course, I said same material and similar use. For example, cotton material, cotton yarn 20 tags, carded, combat version, carded version, combat version, open and yarn version. Yeah, different technologies. Well, we said this is our equation, our final equation. Case 1 is the case same technology and different ion counts. Koechlin said that for different ion counts is good when the ion have a geometrical proportion, when we accept the geometrical similarity. Therefore, corresponding angles shall be same. This idea, this Koechlin's idea, 200-year-old, is very, very good also in these days. It's very good idea. But we must think now about the beta d angle on the surface of our yarn. Nevertheless, on the angles which have the axis of peripheral fibers. Axis of peripheral fibers have angle beta dash. Yeah? So that this assumption, which is maybe very good, we must interpret angle beta dash for all of this yarn must be constant. Well, because beta dash is constant, rho, say material, for pi, total constant, q for given material is constant, so R is constant. A resulting recommendation for such yarn from same technology and different yarn counts, R shall be constant. For suitable twisting, R must be constant. Let's solve the second case. Different technologies and same yarn count. The contact density, density of contacts, number of contacts per volume unit, should be constant, because the mutually influence fiber to fiber and so on, we use it for, we said we use this yarn for a similar analogical use and so on. Because a number of contacts shall be same, because number of contacts is parameter times mu square. We know it from earlier lectures. Then also packing density shall be same. So let's twist carded, combat, as well as open-end yarn. So same yarn count, so that it will have same packing density. Then left-hand side of our equation is constant. Same packing density mu, yeah? Denominator of right-hand side, we compare yarns having same yarn count. It is from same material. So denominator is constant too. And because this equation is valid, also R must be constant. Evidently. Yeah? Understandable? Left-hand side, we say is good for suitable twist to have packing density constant. Whole left-hand side of our equation, therefore, all this left-hand side is constant. Denominator, because all yarn counts are same, is constant too. And because this is equivalency, therefore R must be constant also. So R is constant. In both cases, which are quite different, we obtain the same result. R should be constant. So let's generalize this knowledge and say that for given material, independently to yarn count and independently of type of technology, of course I speak about the technologies using twist, for another glue fiber to fiber together and obtain some linear product there. The spinning technology used twist, no bonded slivers or something. So for each material, the quantity and use of our yarn, the quantity R must be constant. What is a good value you can see in this table. For example, for cotton fibers, long staple 2.1, takes power to 1/2. Medium staple 2.7, and so on and so on and so on. So we have couple equations. This is the first and this is the second. This couple call my students horrible Neckar's equations. In Czech language it is šílený Neckářovy rovnice. In a shortening it is sh, n, r, s, and r, and one times one girl, one student will come to my assistant and ask please she for some consultation. And my assistant say yes, and what the theme of which was, where is your problem? And she said, I want to have the consultation about Schoner. Horrible and scarce equation. So it's very known in my on my university. Schoner is very known. Professor Ishtiaq can comment it more. You know it very well. Yes. How is possibility how to apply this couple of equations? Usually we know Q and R. Maybe when you don't have more precise values, you can use some values from my tables. So you know Q and R, then we know T and rho, fiber fineness and specific mass, the mass density of fibrous material, and we also know the required Young count T. How to evaluate, how to calculate the future quantity of our yarn. At point 1, to calculate right-hand side of equation 2. Is it possible? Yes, without problems. Point 2. Find the packing density mu as a root of equation 2. Other word, find the mu, so because the left-hand side was given the same number as our earlier calculated right-hand side, using numerical method, tables, prepared before, and so on. Then we know mu. Point 3, calculate the left-hand side on the equation 1. We know mu, we can calculate the left-hand side value. And point 4, find the suitable yarn with Z as a root of equation 1. We know all right-hand side, Q, yarn fineness, so Z is trivial to explicitly to evaluate, isn't it? You know, Z square is what? This by this and by T, Q and T power to 1/4 times the square is 1/2, isn't it? Yeah. So trivial. It's trivial to obtain Z from this equation. So we obtain Z as a suitable twist of our yarn, and calculate the yarn diameter using packing density, which we derived from the equation from lesson 1. So it is the way how to practically to use this couple of expressions. An example is here, numerical example. You can home study and verify that I calculate it well. The problem which can you have is the problem in practical application in evaluation in the point 2. Find the packing density mu as a root of equation 2. Find the mu on left-hand side because we validate the equivalency with known right-hand side. You can use tables, you can use a numerical method, and you can use also approximation. Similarly, we spoke about the approximation of our first equation, but it's possible to approximate also our second equation. How the recept is here. It's presented as a recept. Both approximations are derived from following using following way. We said in some point in the first section it was mu star. In some point, the approximation equation must give the same value than the original. And the second assumption for approximation is, or the second necessity is, the first derivative of approximation function and first derivative of original function in our point must be same. And based on these two equations, equivalency of value and equivalency of first derivatives, we obtain the final equations which are present. I am presenting now here. So we can calculate following. We must evaluate the quantities of z star, t star, and mu star of middle yarn from equation 1 and 2. One yarn, let's say, okay, one yarn I will calculate based on original equations, include, I don't know, tables or numerical method and so on. Only one yarn. One typical average yarn which is in the middle of area of my activity in my spinning mill. Yeah? This yarn, this average or middle yarn, values have stars here. The value I using all this and the recipe which I presented. Now we evaluate the value b, because we know mu star is possible. Then capital B, also possible. Xi, also possible. All the three are helping quantities on our way. Then Q, it will be very important. And alpha Q according to this equation. Having these quantities, we can formulate the approximation equation that the yarn twist is alpha Q times t power 2 Q. Yeah? An example, numerical example, show that the correspondence between this is a numerical example, and this is a graphical interpretation of two curves. One is alpha, recommended alpha as a function of yarn count. Two lines, one is original theoretical equation, the second is approximation. Using that in large interval, the both versions are no identical, but practically same. Very good for application. Okay, that's all for today. I presented you some model of packing density. I presented you a couple of horrible net scarce equation, and in short also the way how to apply it in praxis, in practical calculation. I didn't explain one moment. I spoke about the yarn diameter, but the question is, what is it, yarn diameter? Because yarn diameter, where is the end radius for a yarn diameter? Where is the maximum radius in the yarn? And where started the areal, the sphere of hairiness of the yarn? In reality, it have not strong borders. Diameter is every time a little the question of our convention, and we need to solve it together with the modeling of external part of the yarn body, which is a sphere of hairiness. So our next lecture will study the models of hairiness, and in connection with this model, we will explain in more details the question about the yarn diameter too. Well, but it will be in my next lecture. Thank you very much for your attention.